Okay, so now let's talk about linearity. So earlier we defined a matrix transformation as a function t going from real vector space to real vector space, meaning like vectors with real number components to vectors with real number components. Um, and we define it to be a matrix transformation if you can basically describe what it's doing using matrix multiplication. And then we showed that because A times CV is that, you can move scalars there to there, and you can distribute matrix multiplication. That means that this is true, that T, you can move the scalar out of a function, and you can split up addition inside to addition outside. So these things are called, these two things are called linearity. So the question then is, well, it turns out the fun fact is any function that's going from vectors with real components to vectors with real components that satisfies those two linear properties can be written, it goes the other way basically, that if it satisfies those two linear properties, then we can write it as t of x equals a of x. So the way to do that is start off with a function t that's linear. So assume t is a function going there to there that is linear, meaning t of cx, you can factor the scalar out, you can split up multiplication, split up addition inside. So then define this matrix A to have the columns t of e1, t of e2, all the way to t of en. So now we're going to show this. So check this out. So t of x then is t of x1, x2, x3, which is equal to t of x1, e1 plus x2, e2. And basically what we're doing from the first step there is like we're writing 1, 2, 3 as like I plus 2j plus 3k using our Calc 3 language. Using our linear algebra language, it's e1 plus 2e2 plus 3e3. Okay, then we assumed that our function was linear, so that means we can factor out scalars, split up addition inside, so do a whole bunch of steps at once, and we're there. And then t of e1, that's the same as a e1 because that's how we defined a. T of e2 is the same as a times e2 because that's how we defined a. But then we've got scalar times matrix times vector, so we can factor scalars back across, and we can factor out the a from everything, and basically doing the opposite of distributing. And then x1, e1, x2, e2, all the way to xn, en, that's just the vector x1 to xn. That's a times that, which is basically a times x. So we just showed that if t was linear, then t of x equals ax, where a is the matrix made by the columns, whose columns are t of like e1, t of e2, so on and so forth. Okay, so this is just saying this officially, what we just said. So a function t from real component vectors to real component vectors is a matrix transformation where t of x equals ax for some n by n matrix A, if and only if t of cv equals c times tv, t of v plus w equals t of v plus t of w. So in this case, A is the matrix whose columns are that. Okay? So next, let's talk about this example. Now we're going to consider the example of the function t going from the real plane to the real plane that rotates the vector x by 45 degrees. So an example is starting there on the left and then graphing where it went to on the right. So 45 degrees, it was kind of there, so we moved it 45 degrees. Okay, so then the question is it linear? Does it satisfy those two things? So we're wondering, is that true? So is it linear? Well, check out, I'm going to do this as a little proof by picture. So then here's v, here's c times v. Here's t of v, here's t of cv. Well, because the angle change is the same there, and so we see that t of cv equals c times tv. All right, and then let's check out the other one. Well, if I've got vectors v and w that add up to the blue line, v plus w, then if I rotate everything 45 degrees, then I still have T of V and T of W, and T of V plus W is equal to T of V plus T of W. So checks out. And so that means that this is a function that we can describe with a matrix. Well, the best way to find that matrix is to do the matrix that has columns T of E1, T of E2. So where does E1 get sent? Where does E2 get sent? Well, they get sent there and there. So let's look more closely at one of them. So T of E1, it's rotated, so it's still the same length. It's still 1. And it's then going to make a 45, 45, 90 triangle. So it has these side lengths, which if you ever rationalize the denominator, you could write as square root of 2 over 2. And so basically, T of E1 is then square root of 2 over 2, square root of 2 over 2. And then if you think about the other one, it's the same except the x component's negative. So negative square root of 2 over 2 and square root of 2 over 2. So then our whole matrix is then this guy right there. Okay, and that finishes that example.